Good morning, sir. Lalit, sir. Good morning, sir. Lalit, sir. Good morning, sir.
Yeah, good morning. Am I audible?
Sir, yes, sir. You're audible, sir.
Yeah. Thank you.
Sir, can we start, sir? HOD,
Yes,
sir?
sir. We can start, sir.
Sir, yes, sir. Good morning and warm greetings to one and all present here. We are happy to start our third AICT ATAL program on the field of electric vehicles. The title, Cutting Edge Technologies in Energy Storage System for E-Mobility. We are very much delighted and happy to welcome all the participants for these sessions. I now request our HOD sir, Dr. V. Kumachinian sir, to welcome the gathering.
Good morning, learned professors. So really happy to inaugurate this 5-day ATAL FDP titled Cutting Edge Technologies and Energy Storage System for E-Mobility. So on this occasion, on behalf of the management, the principal, CE sir, the Department of EEE, and my own behalf, I am very much happy to welcome you all for this 5 days ATAL FDP, and which is going to be held between 14th to 18th of this June. So which is going to spread across the 14 sessions, and at the 15th session, we are going to conduct the assessment, and based on the assessment marks, you are going to get the certificates. And definitely this 14th session is going to be very much useful. So in this series, the first session is going to handled by the reputed scientist, Dr. Lalit Singh from the Nuclear Power Corporation of India Limited, BARC, Mumbai. So I welcome you, sir.
Yeah, thank you.
And I'm happy, and the team EEE is happy to welcome all the participants spread across the Pan India. And definitely this 5-day FDP is going to be a great breakthrough in the knowledge sharing as well as the knowledge acquiring for the teaching community. So we are all hoping this EV is going to play a major role in the years to come, as per the report by the NITI Aayog, and the government of India is also giving a great push because of this forex reserves depleting and etc. due to this importing of the oils. So definitely the future is going to be with the electric vehicle. Definitely all the participants is going to get the necessary inputs from our resource persons. We are assuring you that, and you are going to enjoy all the sessions. So with this note, I am very much happy to inaugurate this 5-day ATAL FDP. And once again, on behalf of this KPR IET team, we welcome you all for this 5-day ATAL FDP. And I congratulate the organizers, Dr. J. Karpagam, Professor of EEE Department, Dr. R. Uttarasamy of Associate Professor of EEE Department, and Dr. P. Ravikumar of Assistant Professor of EEE Department for coordinating this one. And I once again thanks the AICT, the ATAL officials, for providing us the opportunity to conduct the third FDP in a series of these electric vehicles. So thanks for the opportunity. Have a nice day and have a great learning. Thank you. Thanks for the opportunity. Good luck to all. Thank you.
Thank you, sir. For the first session, we have with us Dr. Lalit Singh sir, scientist from NPCL BARC Mumbai. Here are a few words from about our resource person. Dr. Lalit Kumar Singh received his PhD degree from Indian Institute of Technology, previously known as Banaras Hindu University. He is currently a scientist in NPCL BARC, Department of Atomic Energy, Government of India, since 20 years, and has a distinction of working on pressurized heavy water reactors and light water reactors. He has an illustrious career and succeeded in several critical jobs assigned to him in his illustrious career, though each of them was challenging. His assignments over the years range from design, development, testing, IV&V related research and site validation of safety critical computer-based system of Indian nuclear power plants. He has published several research papers in journals of high impact factor like IEEE Transaction, IEEE Computers, ACM, etc. He has been invited for chief guests, keynote speeches, session chairs, and talks in many international conferences, short-term courses, workshops, and faculty development programs from many IITs, NITs, and other institutes of national importance. He is a recipient of many awards like Publication Award, Group Achievement Award. He is a reviewer of several SCI index journals of high impact factor. He is a life member of Indian Nuclear Society. He is a founder member and industrial coordinator of Proposed Center of Dependability at IIT. He is in the panel of faculty assessment committee for Department of CSE IIT Roorkee to assess their research profile and give recommendation. He is a member of editorial board of many reputed journals and guest lead editor of many special issues. He is supervising many PhD students of different IITs, NITs, and is PhD thesis examiners for IITs, NITs, and other reputed institutes. He is an expert member of industry policy transformation of IIT Ropar, board of studies of many autonomous institute, and member of advisory board of many institutes and university. He is a reviewer and project collaborator of research proposal of Board of Research in Nuclear Sciences. He is also a faculty of Nuclear Training Center, Department of Atomic Energy, Government of India. He is interfacing with other countries like Russia, USA, France for importing nuclear reactors that are based on new technologies. His research interests are in the area of reliability, safety, and security of safety critical computer-based systems. So far, he has completed 33 projects of Department of Atomic Energy, Government of India. Sir, we are really proud to have you amongst us, and I cannot wait much longer, and I leave the session to you, sir, to hear from you. You can
Okay.
kindly take over the session.
Yeah, so thank you for introduction, and I would also like to thank all the organizing committee members who has provided me this opportunity to share some of the experience to all the participants. So to start with, let me share my slides. Uh, so are my slides visible?
Yes, sir. It's visible, sir.
And it is changing also?
Yes.
Okay, thank you. So I'll be talking on safety analysis of mechatronic systems. And so mechatronic systems are basically widely used in various critical domains, for example, in vehicles, electrical vehicles, or in nuclear domains, or in space domain, military domains. And these systems are very safety critical in nature, because the failure of these systems can lead to the catastrophic disaster, or even it can lead to the loss of human lives. And hence, it is very much necessary to uh, address or to perform the safety analysis of such kind of systems. And so to start with, let me go through the today's outline. So we'll talk a little bit about the safety, what is the background of the safety. Then I'll be touching a mathematical formalism known as Petri nets. And the concept was introduced by C.A. Petri in 1960, who was a German PhD scholar. And he introduced this concept to model the dynamic behavior of the system, or the dynamic processes. So if you want to categorize the processes, it can be done into two types. One is the deterministic processes, and the other one is the stochastic processes. And deterministic processes are those processes, the outcome of which can be 100% guaranteed. For example, suppose I do have a pen in my hand, and if I drop a pen on the ground, I can 100% sure like it is going to fall down on the earth. Why? Because of the gravitational force that is acting on it. So these processes, I mean the outcome of these processes are guaranteed, but there are several processes whose outcome cannot be guaranteed. And for example, it's suppose I want to catch a flight to attend a meeting at Hyderabad at 5 p.m. and considering all the traffic conditions and all the overheads, possible delays at the local traffic or airport or the aero traffic, I plan accordingly, and but then also I may miss my target. Why? Because of unexpected delay or unexpected scenario. For example, the cancellation of the flight on that day because of some heavy rain. There could be many reasons. So what I mean to say, in spite of a rigorous planning, we may miss the target. And when we talk about the reliability, even human being is also stochastic in nature. So definitely all the creation of the human being or the systems that has been created by the human being will be stochastic in nature. And so Petrinet is one of the very effective model to capture the dynamics of that system. So if you see, like, all the systems are dynamical in nature. So we will talk something about this battery net. We will see what is a working mechanism and what is the basic building blocks of this battery net. And then we will be taking a case study and then we'll perform the safety analysis on that case study using the battery net modeling. And then we can conclude our session. So if you see, like, the computers, these are used as a passive and active component. The passive generally is used for the monitoring purposes and active for the controlling purposes. And there are, we almost in every domain we make the use of the computer to control and monitoring purposes. And hence, when we talk about the safety analysis, though, definitely we have to consider the software components as well. So, and the whole idea is to perform the safety is I should be able to stress my system, and then we can see whether there are any hazardous states in the system, and then I can propose some of the remedial action to avoid that hazardous station or states. So an important fact is that software does not harm anyone, but it can control the hardware, and definitely if it is not able to control the hardware as per the intended functionality, the hardware can harm or it can damage the things. And therefore, as I said, software safety also must be considered as a part of the overall system safety. And let us switch to the battery nets. As I said, the concept was introduced by C.A. Petri, who was a German PhD scholar in 1962, to model the stochastic behavior of the process. And after going through the thesis, MIT USA was trying to explore whether this modeling construct will be able to model the concurrent systems or the parallel systems, because in 1970s there was an era where the people were striving to develop the concurrent or the parallel systems. And with this objective, they conducted a conference in 1970, conference on concurrent systems and parallel computation. And the conclusions were very beneficial, and the people started taking interest and to explore the possibility of strengthening the model further to solve more challenging problems. And with this objective, again, they decide to meet after 5 years. And in 1975, MIT USA conducted a conference on battery nets and related methods. And then it started gaining popularity, and the industry also started using it for modeling purposes. And looking at the demand in the industry, Germany started a course on general net theory of processes and systems in 1979. Then the people from diversified domains were also trying to explore whether this model will be able to capture the stochastic behavior of the systems of their particular domain. And with this objective, in 1980, first European workshop on applications and theory of batteriness was conducted in France. And then people started coming out with different flavors of batterynet depending on the context of the system. For example, if I want to work on the real-time system, definitely the timing information plays a very important role. And for that, the specific flavor of the batterynet known as timed batterynet is there. So the first international workshop on timed batterynet was conducted in Italy in 1985. And there are so many other flavors of the batterynet, but although this is not an exhaustive list, but I just wanted to cover this slide to let you all know the important milestone by which batterynet becomes so popularized, and what are the various capabilities of this modeling construct. And if you look into the application, it can model almost all kind of applications. And now let us go through the working mechanism of the batterynet. And suppose, for example, I want to model a very small, very basic chemical reaction, that is hydrogen plus oxygen that gives water. And it's a very basic chemical reaction, and we all might have studied in class 9th or 10th. So let us see how we can model this chemical equation with the help of the batterynet. First, before that, let us see what are the basic building blocks. So if you are able to see the figure, this figure is a batterynet figure, and we start with the basic building blocks. So if you are able to see the big circles, there are the three big circles in this batterynet figure, and these big circles are known as places. So I'm using one place to represent hydrogen, one place to represent oxygen, and one place to represent water. And then you are able to see the rectangular box, which is known as the transition. So there is only one transition in this figure, and there can be a connection between the places and transitions and places. But there cannot be direct connection from places to places or transitions to transitions. Now, the places and the transitions can be connected by the directed arc. So there are the three directed arcs, if you are able to see in this figure. One is connecting hydrogen place to transition T, other is oxygen place to transition T, and one is from transition T to water place. And then you are able to see the weight, the numeric number that is assigned on the arc. And this numeric number is known as weight of the arc. So the weight of the arc which is connecting hydrogen place and transition T is 2. And which is connecting oxygen place and transition T is 1. And transition T to water place is 2. We will see the significance of this weight while we will be seeing the working mechanism. Now the next important building block, you are able to see the small embedded circles inside the places. For example, hydrogen place contain two circles, and these circles are known as tokens. And the tokens are used depending on your system context. For example, here I'm using to represent the number of atoms because the hydrogen contains two atoms, so I'm representing it by two tokens. Similarly, oxygen contains two atoms, so I'm representing it by two tokens. And now, an important information is that the distribution of the token among the places represent the state of the system. For example, in this figure, what is the distribution of the system? It is 2, 2, 0 because hydrogen place contains two tokens, oxygen place contains two tokens, and water place contains 0 token. And now, so this figure is representing the left-hand side of this equation. That is 2H2 plus O2. And now it has to be converted into the water. So it means now we have to change the state. And as I said, the state is represented by the distribution of the tokens. So it means that the token distribution needs to be changed. But there are the rule to change the distribution of the token. And the rule says that any transition, at least one transition in the given pattern at figure must be in enabled state. And so what is the enabled criteria of the transition? And that is that all the input places must contain sufficient number of tokens. For example, with respect to this transition T, there are the two input tokens. So sorry, two input places. One is the hydrogen place and another is the oxygen place. And these two places must contain sufficient number of tokens. And what is the criteria of the sufficiency of the token? So that will be decided by the weight of the respective arc. Now you can see the weight of the arc is that is connecting hydrogen place and transition T is 2. So that means the hydrogen place must contain at least 2 number of tokens. And the weight of the arc which is connecting oxygen place and transition T is 1. So it means oxygen place must contain at least 1 number of token. I have not put any numeric number on this transition. So by default, it will be treated as 1. Or if you want, you can keep numeric number 1. Okay. So if you don't put any numeric number, it will be treated as 1. And so here you can see the transition T is enabled condition because all the input places are containing sufficient number of tokens. And so it is in enabled condition, and when any transition is in enabled condition, it fires. And after firing, the token starts moving from the input places to the output places. But how many tokens will be moved out from the input places and how many will be deposited to the output places? That will be totally governed by the weight of the respective arc. So here, for example, in this figure, the weight of the arc which is connecting hydrogen place and transition T is 2. So after firing transition T, the 2 tokens will be moved out from this hydrogen place. And 1 token will be moved out from this oxygen place because the weight of the arc that is connecting oxygen place and transition T is 1. So in total, 3 tokens will be moved out if I'm summing up the tokens from all the input places that are moving out. and how many will be deposited into the output place. So for the transition T, water is the output place. So how many will be deposited, that will also depend on the weight of the output arc. And here in this figure, you can see the weight of the output arc is 2. So the 2 token will be deposited in this water place. It means there is no law of conservation of tokens. So although the 3 tokens has been moved out from all the input places, if I it's summing up, but only 2 tokens are deposited in the output place. And then it will become like this. So 2 tokens has been moved out from hydrogen, 1 has been moved out from oxygen place, and 2 has been deposited into the water place. And now I want to introduce one more important concept known as the reachability graph. So reachability graph basically it represents all the number of possible states that a system can reach throughout its operational life. So for example, you can see there was this was the one state where a state was can be represented with the help of the token. So 220 was the initial state, and then after transition T, the state has been changed from 220 to 012. And now you can see this transition is no more in enabled state because hydrogen place is not containing any number of tokens, although oxygen is containing. But I said all the input places must contain. So that was the working mechanism of the PatriNet, and now I'll be taking a case study of reactor control, reactor protection system. Although the methodology can be used in any of the mechatronic systems, but here I am taking a case study of the reactor protection system, and which is a complex control system comprising several safety electronic and mechanical components known as nuclear safety components, and it is used to shut down of the nuclear reactor, and hence it is also known as shutdown system. So first let us see how it works. So this is a figure of the system, and let me explain the working mechanism of this system. Then you will be able to model that system using PatriNets. So if you are able to see on the right side of the figure, there is a spherical shaped structure known as calandria, where all the nuclear fission reactions taking place. We know like nuclear fission reaction takes place, which is a chain reaction for generating of the power in nuclear power plants. So here what happens like, any uranium, because uranium has a big, is very heavy nuclei, so it can undergo spontaneous fission, and when it fission, then some radioactive elements comes out, and heat energy in one reaction, 220 million electron volt of energy, heat energy comes out, as well as 2 to 3 neutrons in one reaction also gets generated. And then these 2 to 3 neutrons again will strike to the uranium nucleus, and each neutron will be able to produce one chain reaction or one fission reaction. And in this way, neutron population keeps on increasing exponentially, and the heat energy will also keeps on increasing exponentially. And hence there is some control mechanism, some control systems which basically controls this heat energy by controlling the population of the neutrons. And in case of the failure of the control system, we have to shut down or we have to terminate the reaction. So this is a system basically which does this. It basically terminates the fission reaction. And how it terminates the fission reaction? We know like neutrons are the responsible for the fission reaction. So it eats up the neutrons. So basically it is eating up the neutrons, and then like so how this phenomenon basically is working. So if you are able to see in the calendria where the fission reactions are there, are keep on taking place, there is a pipe, there is a mechanical pipe which contains so many tiny holes, and from these tiny holes the poison can be injected. Poison in the sense which can eat up the neutrons. So we say it is a liquid poison. So the poison can be injected, and how it will be injected, let us see the instrumentation logic. So if you go back from this pipe, and you'll be able to see it is connected to a poison tank where the poison, liquid poison is there, and on demand it can be injected into the calendria. And because of these tiny holes, it will be populated to the entire calendria. So it will be able to kill the neutrons in the entire space of the calendria. Now you can see this poison tank is containing one floating ball, which is a plastic ball. This is basically for the smooth injection of the poison, so that the liquid can be injected in a equilibrium state and the integrity of the entire system can be ensured. So now if you look back, when this so ultimately the requirement is, whenever I want to shut down my reactor, there must be some provision to pressurize this floating ball, which can pressurize this poison and can inject that poison into the calendria. So now who will pressurize? For that, what are the basic logics? So to understand that, just backtrack with this poison tank, and you are able to see it is connected with some set of valves, and these are known as quick opening valves, and some are also known as vent valves. I will show I will explain the each and every valve and the basis of these valves basically. So let us complete the circuit. So so that these valves are connected with the helium supply tank, and which contains the helium, and which can pressurize whenever I want. I can pressurize because helium contains good pressure. So I can open the valve and I can press. So automatically this helium will pressurize the floating ball, and the poison will be injected into the calendria. And moreover, the basis of the helium, why the selection of the helium is, it is also an inert gas. So it will not react to any chemical process, and the entire chemical process will be, the integrity of the entire process can be ensured. Now let us try to understand the basis of these valves. So see, there could be only one valve in spite of these several valves. And what could I do whenever there was a need to inject the poison? I can open that valve like a tap. Whenever I need a water, I can open the tap. Whenever I don't need water, I can close the tap. and pressure is already there, building is already built up into the pipeline. Similarly, we could do in this case also. So I could have only one valve, and I could have opened on demand of the shutting down of the reactor, and I can close when I want to restart my reactor. But what could be the basic problem with this? Suppose there is a one valve. If that valve is stuck to open, whenever I want to shut down the reactor and I want to open the valve, there could be some failure of the mechanical failure in the valve, or there could be some relay failure, which is basically energizing the relays to open and close the valve. There could be some electronic circuit failure. So what we can do? It is better to apply one more parallel valve so that we can ensure if one is not able to get open, at the other one can be open, and the helium supply can be passed from the other valve, and I could serve my purpose. So, but then why we need more valves? What is the purpose of more valves? So, the purpose of the more valve is, for example, suppose I have injected the poison, and now I have rectified the entire process, and I want to restart my reactor again. And if suppose any of the parallel valve is because when I want to restart, I have to again close that valve. And if suppose it has some mechanical failure and it got stuck to close, or some relays like failed, then what could I do? Here the failure mode is different. The earlier failure mode was stuck to open. Here the failure mode is stuck to close. Then what could I do in that sense, in that scenario? So just apply one more valve in the series, and that will take care the failure mode stuck to close. So if one is not able to close, the other one will be able to close, so that the line can be blocked. And hence, in both the parallel lines, we have to apply these mechanical valves. Now, it's okay. So 4 valves are up. I'm convinced now 4 valves are enough. Then what is the purpose of these 2 valves, which are basically on the vertical side of each line? Now let us try to understand the basis of these valves. So suppose when the reactor is in normal operating condition and we don't want to shut down the reactor, so all these 4 valves will be in closed state, right? And suppose because of some mechanical failure, the one valve is leaking. Any of the valve is leaking. So what it can do? It can build up the pressure in that line, which can jeopardize the integrity of the other valve. And if it gets success, it can create a pressure on the floating ball in the poison tank, and which can inject the poison. So although I was not wanting to close or to shut down my reactor, but then also it is, and it will be a huge economical loss. So what I can do, let us apply one vent valve so that if any pressure is built in case of leaking of one valve, it can be released into the atmosphere. And similarly, the vent valve has to be placed in other line to handle the same scenario, right? So I mean to say, if you see like in this, so what we can do, the working mechanism would be in the normal state when I don't want my reactor to shut down and it is under operation. All these horizontal valves, which are known as quick opening valve or the fast acting valve, are in closed condition, and these two vent valves always are in open condition. So whenever there is a demand to shut down the reactor, first I'll have to close the vent valve, and then I'll have to open all the quick opening valves. Why I need to close the vent valve first? Otherwise the pressure would be, all the helium pressure would have been gone to the atmosphere, and we could have wasted the helium, and the safety will be jeopardized because it was a demand to shut down the reactor, which could not be done. And when I want to restart, then again the reverse logic needs to be done. So I'll have to first, open the vent valves and then close this, all the horizontal valves. Now, if you see in this working mechanism, other than the valves, all are the static in nature. Only the valves are dynamics, and hence there is a lot of concern about their correct operation of these valves, because there is some instrumentation logic, the software is also playing role, and all like these are working on some interlocks. Uh, so we have to really deal with that. So for the safety analysis, let us perform to prove the correctness of functioning of these valves. Let us try to model these valves using the Petri net. Okay, so this is the Petri net model of that valve, of those dynamics of the system. And you can see like TPD. Let me explain this Petri net model. And before that, one interesting fact is that here all the arc, no arc is having any weight. So by default, all the arc is having weight 1. Okay, so here TPD is a place which represents that trip parameter have been deviated. Trip parameter in the sense there is a demand to shut down the reactor. For example, in the human being, there are a lot of process parameters like blood pressure, heartbeats, oxygen level. And if it gets deviate from the normal range, definitely it is risky. So we have to take the medicinal drug to control that. And similarly, so these are the trip parameters for human beings. Similarly, there are the various process parameters which are trip parameters in the reactor, and suppose that parameter got deviate, and which is represented by a token in the TPD place. Then TTPD, it represents that it sends the signal to create a logic condition and to energize the relay to close the vent valves, because the first thing is we have to close the vent valves. And what is a logic condition? Logic condition is just like a flag. Suppose I want to do some construction or maintenance work on the road. I can put a flag, red flag, and write road construction is under process, so that whoever the travelers are trying to pass from that road, they can deviate. And hence this is what here the logic condition is. It is a signal. So when the let us see, from TTPD, the token can move to DLC on, which basically represents that logic condition has been created. And after that, it has to be on the hold condition. So TLCH is basically the logic condition is on hold condition. And when this token reaches to PLCH, it means now it was the trigger to hold logic condition needs to be in hold condition, and now when the token will be reaching a PLCH, it will be denoting that logic condition now has been set to hold a condition. Okay, now let us see the vertical path. Just a moment, let me, I'm getting a call. Yeah, hello. I'm Yeah, I'm sorry, I was getting a call. Yeah, so we have just created the logic condition in the model, and now let us try to, once we have created the logic condition, we have to operate the worlds. So in the vertical, you can go to the vertical path where the place PREVV, it represents that the relay has been energized to close the vent valves, because the first thing is we have to close the vent valves, and then this trigger PVVC, it will represent like it triggers to close the vent valves, and when the token comes in PVVC, it will represent that the vent valve has been closed. And after closing the vent valve, we have to open the fast acting valves or the quick opening valve. So I have I have initialized the token in PFAVC, which basically was representing that this fast acting valve was in already closed condition, and if it is already in closed condition, then only it can pull the token and deposit in the output place, which represent that fast acting valve will be in open state. So this is my injection process. Now I want to, for example, I want to restart my reactor, then coming after maintenance activity, then coming back to the horizontal line where the logic condition was on hold. Suppose the logic condition was I have to turn now off, and once I will trigger logic condition off, which is represented by TLC off, the token will be moved to PRDBB, and it represents that the relay de-energized to open the vent valve, and PVVO, it's because I have to do the reverse logic for restart my reactor. So TVBO will represent that I have triggered to open the vent valve, and after opening the vent valve, I have to close the fast acting valve. So for that, I'll have to trigger TFABC, and that will close the fast acting valve. So this is the entire process that we have modeled in the battery net. But one more interesting point, we have not considered these two places known as PFABCD and PFABOD. These are just the redundant information about the state of the fast acting valve, whether it is in closed state or is in open state, and which is coming from the redundant sensor, because it is a safety system, so we cannot rely on the one sensor, and hence the redundant information is coming from the different sensor of the same system, because fast acting valve is an important object to consider. Now, so this is my model, and I want to address the safety of the in that model. So what is the whole idea is? The whole idea is to first create a reachability graph. And reachability graph, when I touched on upon when I was discussing the working mechanism while explaining the basic chemical reaction, hydrogen, oxygen, water chemical reaction, then it represents the possible number of states that can occurs throughout the operational period of system. And states basically are the representation of the tokens. So whoever the places that contains the tokens, only those places will be responsible to change the state of the system. For example, in this figure, the tokens are only in 3 places. One is PPD, one is PFABCD, one is PFABC. So this is the one state, this is the initial state, and you can write down by S1, and here we have written these places: PPD, PFABCD, and PFABC. Now going back to the same figure, you can see in this figure, one transition is in enabled state, that is TTPD, and hence the token will, and hence this transition will fire, and after firing of this transition, the token will be moved out from PPD place and will be deposited to PLC on and PREBB. So here just PPD has been replaced with PLC on and PREBB, because the token has been moved out from this place and deposited in these 2 places, and the rest of the places has been written like this. And similarly, we can further keep on reducing the states till we reach all the states in the system. And now we have to analyze each and every state with respect to whether is any state risky or every state is safe. It is like this. For example, the human being can have various states like eating, sleeping, moving, walking, and meeting accident. Now, other than meeting accident, all our states were the normal states or the behavioral states. But meeting an accident is an accidental state, which is a risky state. So here, we have to just analyze each and every state and try to find out whether there is any risky state. And after that, we'll have to find a provision where we can ignore these states, avoid these states. So if you are able to see in this figure, the 2 states that I have identified as the risky states, one is S3 and one is S6, representing by the solid rectangle on the left upper part. And let us see why these are risky states. So first consider S3. In S3, you can see there are the tokens in PLCH, PREBB, PFABC, D, and PFABC. it means PLCH means it means the logic condition is on hold condition, and so the fast acting valve should always be in open condition. But here in this state, it is showing like it is in closed condition, so it is a risky state. So that is why I have marked. Similarly, if you analyze as 6, you can see the there is a token in PFAVOD, which were representing that fast acting valve is in open state. And there is a token in PFAVC also, which is representing that it is in closed state. So to whom I rely? So this is a conflict state, and so I need to mark this state as a risky state. And other than these states, I don't find any other state as a risky state. So now what I need to do to overcome these states or to handle these states? If you first let us consider S3. Now you can backtrack the S3 and you can see it is coming all the way from S2. And from S2, there are the two transitions which are fired or which are in parallel. And hence these transitions are known as in race condition. So one is leading to the risky state, that is S3, and one is leading to safe state. So what I can do, whenever these two transitions are in a parallel state, I can prioritize one transition. So I can prioritize TVBC so that I can always avoid the S3 state. Similarly, for the S6, you can backtrack and you can see like it is coming all the way from S3 and S4. And S3 we have already avoided. So it is there is no point coming from S3. But from S4 again, you can see there are the two parallel transitions. One is reaching to the S6 state, which is a risky state, and one is to S7 state. And hence, we have to prioritize the transition that is TFAVO, which is leading to the S7 state. And if we are able to do that, we are able to avoid the risky state. And now let us coming to the implementation part, how we can do that. So these two states were the risky states or the threatening states. So we basically how in the model we can do that, how we can prioritize the TFAVO with TLCH. Just connect from the TFAVO and put an additional state, and that connect that state to the transition whom I want to give the less priority. And similarly in the case of TVBC and TLCH, so that I can ensure TLCH can only be fired when there is a token in I1 and I2. I think both has written I1, IE, but one is I1 and one is I2. It was a printing mistake. So, so it means then I can 100% sure, yes, TFAVO and TVBC will always get the first preference whenever these are in the race condition with TLCH. So this is, it means I have handled this in the model. And now let us see the implementation. So how we can do. Now again draw the reachability graph. And after drawing the reachability graph, we can see this is the graph that we are seeing. And here we are not finding any risky state. It means it is fine. But our story doesn't end here. We have to go for the optimization as well. It may because inclusion of the additional plays will increase the number of states, and that will increase the computational complexity exponentially. And we can see like these I1 and I2 were the additional states. It is not performing any role to achieve the functional requirements. And hence, what I can do, I can take first I can ignore I2 and I can consider only I1. And then I can draw the reachability graph and see. We can see like if all the states are safe states or any state are risky. And if any state is risky, then I can do vice versa. I can put I2 and I can ignore I1. And in this way, there could be a possibility that with only one additional place, I could serve my purpose. I could ensure the safety. But if then also if I'm not getting any, say, and then also if I'm getting any of the risky states, then there is no option at all. We have to go with this model. So what I can do is, when I consider only I1, I got again one risky state, and hence it is not serving my purpose. And but when I go for the with only I2, so here this is I'm getting this state, and no state is risky states. Okay, these three states which are marked by the circles are basically the end states. These are not risky states. Now let us try to talk something about the implementation logic, how we can achieve that. So we know like RTOS, or the real-time operating system, it provides a feature to the application software through which we can prioritize the tasks. Therefore, the other way to impose the precedence among the parallel transition to avoid the risky state is to enforce the firing of the transition as per the defined priority. So what I can do, I can put a constraint. How I can do, it can be done by enforcing the timing constraint in the design itself. So this minimum DLCH should be greater than maximum of TFAVO. This is a constraint which always ensure that this TFAVO will be fired always. And hence, this constraint must be checked by the hardware or the software logic as per the requirement. And if the system fails to meet this constraint, the logic must be built in the design such that the control reaches back to the originating state of the risk state. And we have to retry the processing meeting the same constraint. And this logic can be achieved by the soft watchdog or hard watchdog. So in case of hardwired system or module, the hardwired logic must send a periodic pulse to the watchdog. The moment this constraint, which was discussed in the equation, that fails, it must stop sending pulse to the watchdog. And then watchdog must maintain the current variable states and the previous variable states. And if it stops getting periodic pulse, it loads all the dynamic variables which are of previous states, so that I can ensure, like, in case of any risk also, I will be in safe state. And the other possibility is to reset the microprocessor IC through the reset pin, and this will reset the system state. And this concept can be implemented in soft watchdog or hard watchdog. Similarly, so in the software system, the software must send a periodic pulse to the watchdog to process in the same manner as hardwired system does. But okay, that's the implementation part, how we can do that. But still we have to look or we have to investigate further with us for more and more issues or further optimization problem, but to solve more and more optimization concerns. And let us assume that my logic condition is created to trip the reactor, and the embedded system closes the vent valves to satisfy the interlock for poison injection. But there is some security threat, and some bad signal has come which is overriding my closing logic. And how I can identify this? By identifying the inconsistent information in the places which is representing the state of the fast acting ball, that is PFAVO and its duplicate and its redundant place, and PFAVC and its redundant state. And there could be a real condition of fault. So we have to build a logic that in either case the system has to treat that my fast acting valve is in already closed state and resend the signal to open it immediately. And this, how it can be done? We have to introduce one safe transition, that is TSFAB, which will ensure this constraint. So whenever any trip parameter it sees and fast acting valve is in closed condition, then also it can pull the token and it can forcefully put the token in the fast acting valve open state. And now again the design can be validated with respect to see whether there are all the risky states or all the states are okay. So how we can do it again? So this is what the reachability graph, by drawing the reachability graph of that figure. And here we can see like all the states are the risk-free states. And there are the three outputs state as shown in the figure marked by solid circle on the left upper side of the state. So similarly, we can improve the, or we can analyze the model for further issues, and definitely it can be a time-taking process, but the effort, but the benefits basically will overweigh our efforts, looking from the safety perspectives. And if your system is complex or bigger in size, the system and the analysis can be done in parts, maybe component by component or maybe function by function. Or you can segregate the important functionalities, and you can concentrate more on the important functionalities for the safety analysis. So you should also understand that all the risks do not have the equal probabilities. So in this way, like we have seen how we can perform the safety analysis of the system, and these are the bibliography which can be seen. So that's all I wanted to share. In case of any questions, I'll be happy to answer those questions.
Participants, if you have any queries, you can ask our resource person. Or you can put it in the chat box. So since there are no questions, I think I take this opportunity to thank Lalit sir for sharing his expertise in the field of safety analysis for mechatronics. So we have one question, sir. Can we do SIL level configuration in networks? Lalit sir?
See, SIL is a safety integrity levels, and basically we do have the 5 safety integrity levels. And definitely it also addresses some of the safety concerns. Here we can basically, the system analyst has to play a role and to identify what are the prime safety important objects, and what are and we can see with the like we can define the safety, or if I want to quantify the safety, we can quantify with the risk, and which is nothing but it is a probability of occurrence of any system and probability of any event and the uh, frequency of occurring of that event. And if you multiply this, it will give you the safety integrity level. So safety integrity level, definitely you can define in under which level this particular event is there. So it only helps in identification or categorizing the events into the various in safety integrity levels.
Thank you, sir. So at this juncture, on behalf of the management, principal, CE, and team Triple of KPRIT, I take it pleasure in thanking once again Lalit sir for sharing his expertise on the safety parameters of electronic devices. Thank you, sir.
Yeah,
We,
thank you.
we enjoyed a lot, sir. We learned new things also. Thank
Yeah,
you, sir.
thank you.
We'll stop. We'll close the session, sir.